Hi, everyone. In today's lecture, I'm going to be covering the concept of geologic time. In a previous lecture, you may remember that we learned about Nicholas Steno, who developed a process known as comparative anatomy. He examined fossil teeth and compared them to those of a modern shark, and proposed that the fossil teeth were the remnants of an ancient shark. A series of concepts resulted from Steno's ideas about how fossils formed, and because the tooth had to be solid prior to being preserved in the rock, Steno postulated that the rock was formed from previously disaggregated sediments. This was one of the first written descriptions of the nature of sedimentary rocks. With this understanding, Steno developed the founding principles for modern stratigraphy, the study of sedimentary layers. While these principles may seem simplistic now, they were revolutionary for our understanding of how the Earth formed, and it resulted in a better understanding of the age and history of our planet. The first principle is known as original horizontality. It has to do with how sediment is deposited at the bottom of large bodies of water, such as lakes and oceans. As sediment is brought into a body of water, it's generally well mixed, and sediment rains down toward the bottom. It tends to do so relatively slowly and forms horizontal layers. We can see these horizontal layers of sediment forming at the bottom of the ocean and large lakes today. As more and more layers are added, the sediment becomes lithified. This is the geologic process that describes the transformation from loose sediment to hardened rock. The process is too detailed for us to describe here right now, but frequently it involves the growth of mineral cements between the grains and a reduction of pore space within the rock. Because the layers that are being lithified are originally horizontal, the sedimentary layers are horizontal as well, unless something has happened to them to change their orientation. Mountain building and other tectonic processes can disrupt the naturally horizontal placement of these layers. In the image on the right, I have highlighted the boundaries between some of the horizontal sedimentary layers present at the Grand Canyon. These rocks are almost entirely marine, showing the varied history of the area, which is now a terrestrial desert. The second principle is superposition, which may be the most useful for our understanding of geologic time in this class. Superposition states that because sediments are laying down in horizontal layers, and because new sediment cannot be physically placed underneath pre-existing layers of sediment, the rock layers at the bottom of a section are therefore the oldest and were laying down first, and as you go up in the section, rocks become younger. In the case of the Grand Canyon, the oldest layers near the bottom are not sedimentary, but consist of the Vishnu schist, a metamorphic rock, and the Zoroaster granite, an igneous rock. On top of these very old basement rocks, which is what we call them, there are sedimentary layers. Superposition allows us to relatively date these layers. That is, we know that the layers at the bottom are older and the layers become progressively younger as you move up the section. It wasn't until the discovery of radioactive decay that scientists were able to put absolute ages on each of these layers. We know that the older igneous rocks at the bottom are around 2.5 billion years old, while the oldest sedimentary layers are about 500 million years old. The youngest layers, right at the top of the canyon, are still 250 million years old, revealing an important geologic truth. No section of rock contains the entirety of Earth's history. Instead, geologists have had to painstakingly reconstruct the Earth's history by correlating sections from all around the planet using rock types, fossils, and now absolute age dates. The third principle that we're going to cover in this course is known as faunal succession. This concept was developed by an individual named William Smith in the early 19th century. Smith was an engineer tasked with helping to construct massive networks of canals, which were being used to transport goods in and out of the British Isles. After some time working the canals, Smith noticed that the fossils were unique to each layer, and that they could be matched from one canal to another, even if separated by great distances. So that is that the relative age dating showed that each time period contained unique species, and the presence of those fossils could help Smith predict what layers of rocks would be below and above the ones that were exposed in the canal. This is the result of the constantly changing fauna on the planet Earth due to the evolution of life through time. So, being able to actually put time onto geologic events was very difficult. In the 1800s, there was a geologist known as James Hutton who was working on this idea. During the 19th century, scientists and scholars alike were trying to determine how old the Earth was, and their answers differed greatly from a few thousand years to a few million years old. James Hutton was looking at stratigraphic structures, such as the one in this image, and which is known as an angular unconformity. It's an exposure that contains two packages of rock at distinctly different orientations, with an erosional surface separating them. Hutton was looking at a number of these different exposures around the British Isles. So the surface highlighted in red is the erosional surface separating two packages of distinctly different aged rocks. Beneath the red line are a series of vertically oriented rocks. These are sedimentary layers, so they would have originally been horizontal and have been tilted up to vertical. Then the surface was eroded and new sediment was laying down on top of it, highlighted by these rocks, indicated by the yellow lines. What happened was that Hutton saw this bounding surface, highlighted in red, and the rocks below were oriented vertically, and the rocks above were oriented not horizontally, but subhorizontally. And he realized that the contact indicated missing time. And if the rocks that were highlighted in blue at the bottom were deposited as sedimentary rocks and are originally horizontal, as defined by Steno's principles, then they must have been lithified, subsequently lifted, tilted up by a mountain building event, eroded, and then submerged beneath the marine realm again, because the rocks in yellow are actually marine rocks, and sediment would have been deposited again on top of that surface. That layers would have been lithified, uplifted, tilted, and eroded to produce the exposure that we see here today. That whole package of rocks must have been tilted a second time because the youngest rocks are not horizontal anymore, and in the modern day landscape was eroded to what we see now. Recognizing all the steps that had to take place to result in this section of rock and others that he was seeing around Great Britain, I was able to determine that the Earth must be very old. I didn't know how old, but the idea of deep time became a core theme in geology. And today, we've age dated the Earth at 4.5 billion years old. Unfortunately, numbers that large are very difficult for the human mind to conceive of. As humans, we have a pretty good concept of numbers in the tens. That's how many fingers and toes we have. And as we start to get into the hundreds and thousands, our ability to imagine a multitude of that level diminishes. And once we get into numbers like millions and billions, our ability completely disappears. So the idea that the Earth is 4,500 million years old, or 4.5 billion years old, is something that's very difficult to deal with. A scale of a magnitude that's very difficult to imagine. And as geologists, we get used to dealing with these vast expanses of time. But that doesn't mean that we're always good at visualizing the immense magnitude of geologic time itself. In order to section out time into periods that are easier to think of, geologists designated periods within what is known as the geologic time scale. Using relative age dating and the idea of deep time, we've been able to develop this scale, which is divided into progressively smaller slivers of time, which indicate periods of time that share some characteristics. The boundaries between these eons, eras, and periods are actually the result of major changes in plate tectonics, large extinction events, or combinations of both, which result in the disappearance of previously common fossils and the appearance of species that have never before been seen. It should be noted that the Precambrian area at the bottom of this timescale constitutes over 4 billion years of Earth's history, a 4.5 billion year history. So I've reduced the size and scale of that so that you can see the details of what is known as the Phanerozoic eon, the last 541 million years, which is where we'll spend most of the semester, because it's the time period in which multicellular life evolves at a relatively spectacular rate. The periods of geologic time are the Cambrian, Ordovician, Silurian, Devonian, Carboniferous, which we break in the Mississippian and Pennsylvanian in the United States. These two names are still used, but they aren't used internationally, so I will interchange the Carboniferous and sometimes say Lower Carboniferous or Upper Carboniferous, which is what the rest of the world says. But in the U.S., we tend to discuss those as the Mississippian and Pennsylvanian, respectively. After the Carboniferous comes the Permian, Triassic, Jurassic, Cretaceous, Paleogene, Neogene, and finally the Quaternary. The Cambrian through the Permian denote an area of time known as the Paleozoic, era of time known as the Paleozoic. The Mesozoic era is the Triassic, Jurassic, and Cretaceous. And finally, the Cenozoic era is the Neogene, Neogene, and Quaternary. It's difficult to deal with the vast nature of geologic time. As an example of this, on your screen are two relatively popular dinosaurs, Tyrannosaurus rex and Stegosaurus. I've used a modern reconstruction of T-Rex that reflects the idea that it had some sort of coat of feathers, which we'll talk about later, at least in its juvenile stage of life. Maybe even as an adult, it had these feathery tissues on the outside. It's a common misconception that T-Rex and Stegosaurus would have interacted, or at least lived together in the time of the dinosaurs, which sounds fantastic. However, in reality, T-Rex lived about 66 million years ago, while Stegosaurus lived around 150 million years ago. Which means, if you do the math, T-Rex lives closer in time to us in the modern day than it did the Stegosaurus. Geologic time is immense. It's at a scale issue that causes students, the general public, and geologists alike a lot of mental anguish. The upcoming video was created to try to put a manageable scale onto the history of